Okay, today's lecture, or this lecture, I shouldn't necessarily say today, has to do with something that is most commonly known as a paired t-test. So it's going to be important for you to understand that a paired t-test is this particular set of hypotheses, and it is also referred to as a hypothesis test on mean difference. Now, I want to clarify something. So this is section 10 point, I believe this is section 10.4. In section 10.1 of the text, we do, and in 10.2, and I think in 10.3 as well, we do a test of hypothesis on the difference between means. And you may remember that the null hypothesis test for those sections is mu1 minus mu2 equal to delta naught. And then, of course, there are those three alternative hypotheses. This is not that. So mean difference, I want to point this out. A paired t-test is always going to be represented by mu d, not by mu1 minus mu2. Although the authors do kind of refer to it this way, but they clarify what they mean by mu1 and mu2. So this is just super important, and you'll need to be able to recognize the difference between means and a paired t-test or a mean difference. So just a little heads up on that. Okay, so what are we trying to do with a test of the mean difference? What we're trying to determine is we're basically going to be having, I'm going to call it two treatments. I'm going to put that in quotes, or you could think of that as two conditions on the same sample. I mean, the actual sample, and not just, N1, N2. There's just one sample, and we're going to take that sample and we are going to subject it to two different conditions. So not every test is set up for this, but this one is. Now, this delta naught, still the same thing. Delta naught is going to be a number. It can be less than 0. It can be bigger than 0, and it is most often equal to 0. We have the usual suspects here for H1. And what you're going to find is that the test statistic is going to feel very familiar to you. So you might recall that in chapter 9 of the text, we did a test statistic that was very similar to this one. So we did a test statistic in chapter 9 that was T naught equals X bar minus mu naught divided by S divided by radical N. That was in chapter 9. So what you'll notice here is we're going to have something very similar. Remember that in chapter 9, mu naught was the hypothesized mean. This here is going to be the hypothesized difference. Right here. Difference. And then we had the sample mean here. Well, this is going to be the sample difference here. So that's what D bar is. D bar is the sample average difference. So it is a sample average. We had the sample standard deviation in chapter 9. This is the same thing. This is the sample standard deviation of the difference. So D bar is like X bar. Delta naught is like mu naught. SD is like S, and N is just the sample size. And these computations here are very similar. They're the same computations, whereas we had X bar equals the sum over every XJ, and the sample standard deviation for the chapter 9 material was XJ minus D bar squared. So it's the same formula. So what's really great about the paired t-test is that you already know how to do it, and it is just a regular t-test from chapter 9. So let me highlight here. Hang on a second. So because it is so similar to what we did in chapter 9, then this is going to look very, very familiar to you. So if I am doing the null hypothesis for all three of these is going to be that mu d is equal to delta naught. And then if it's a two-sided hypothesis test, then this is how you get the p-value. If the test statistic is positive, it's twice the area above the p-value under the t-PDF. If the test statistic is negative, it's going to be twice the area below the test statistic under the t-PDF. And of course, this is what my two-sided alternative hypothesis will look like. It's that not equals to. If I have a one-sided upper, then my alternative hypothesis is going to be mu d is bigger than, whoops, that should have been a delta naught, sorry, bigger than delta naught. And it will be the p-value will be the area above the test statistic under the t-PDF. And if my alternative hypothesis happens to be a one-sided lower, then that would be mu d is less than delta naught. And of course, the p-value would be the area below the test statistic under the t-PDF. So let's go ahead and jump into an example. I actually have a couple of different examples here. This first example is a civil engineering example. And I like it quite a bit. What we are doing here is there are two different ways of measuring the shear strength of a particular steel plate. And one method is called the Karlsruhe, I'm not sure I'm saying it right, method, and the other is the Lehigh method. So what we're going to be doing here is we're going to be taking one sample. So let me make sure we have one sample of 2, 4, 6, 8, 9. So we have a sample size here of 9. We have one sample of these 9 steel plates or girders. That's what it is here. And there are two conditions. So there's two conditions or two treatments, as I said. So the first treatment is I'm going to use this Karlsruhe method to measure the shear strength. And the second one is going to be this Lehigh method. Same girder, two methods. And then what I'm going to look at is the difference here. So this column here, this DJ, is going to be the difference between this column and this column right here. So for example, this 0.328, that is 1.365, the measurement under the Karlsruhe method, minus 1.037, the measurement under the Lehigh method. Now, it really doesn't matter which one is the first column or the second column, but you have to set up your hypotheses test just right to reflect whether or not you're interested in if this difference is 0 or less than 0 or bigger than 0. So we can actually put all of this data into our calculator and come up with the all of the numbers using the calculator, which is pretty great. But first, let's go through the 8-step hypothesis testing procedure and set it up properly. What they want to do is they want to determine whether there is a difference, any difference. So they're kind of saying a two-sided test there between these two methods. So is one of these methods measuring differently than the other? It's kind of like, think about if you weigh yourself on two different scales and you know, you might say, well, you know, the scale that's at the gym, it always seems to weigh me higher than it does at home. Very similar case because you are part of your one sample of one. All right, so how are we going to do this? My population parameter of interest here is mu d, which is the mean difference. So we're looking to see if the one method measures their average is different than the other. This is not difference between means. My null hypothesis, because they said specifically, determined whether there is any difference, that's sort of code for, oh, it is not equals to here. And they didn't say if the difference was a particular value. So they have identified here for me that delta naught is equal to 0. They also said, please use a probability of type 1 error of 0.05. And my test statistic is going to be this T-naught test statistic, where I'm going to take the average difference minus delta naught, which is going to be 0, over the standard deviation of the difference and divided by the sample size. So, and we're going to reject it if the p-value is less than alpha. So here's here are my computations. If you look at the average, let me go down here, right here. If I look at this difference column, so once I have this difference column, I do not care about this at all. So if I put all of this data into my calculator, I'm going to find that the average here will be that 0.125 plus. I'm going to do that 9 times until I get to 0.507. Then I'm going to divide by n, and I'm going to see that D bar for this, for this particular problem ends up being that ends up being 0.2739. And if I wanted to do the sample standard deviation of this column, how would I have gotten that? Well, that would have been the square root of, I would take each one of those values. So I'd start with 0.125, subtract D bar 0.2739, square it, and then I'll do that for all 9 terms, so that my last term would be that 0.507 minus, sorry, this is so cramped, 0.2739 squared, and then I would divide by n minus 1, so 9 minus 1. And when I do that, I'm going to find that my sample standard deviation of this third column here, I guess it's the fourth column, is 0.1351, 0.1351. So I've got those values. So now I can pop back over here to my hypothesis test, and I'll write this down. So D bar was 0.2739, and they did not provide me with the units on this, sadly. And the sample standard deviation of that difference worked out to be 0.1357. And so if I compute T naught, so I'm going to plug in all of these values here. We know that n was 9. Then we end up with a test statistic that is 6.0819. 6.0819. And if we were to plot that, it's positive here. So 6.0819, that's my test statistic. Then I know that because it's a two-sided test and it's a positive test statistic, that my p-value will be twice this area. So this area must be 1/2 the p-value. And if I wanted to get the p-value the hard way, I could just say, well, the p-value is going to be 2 times the area above this value. So that would be the TCDF in your calculator going from 6.0819 up to infinity for 8 degrees of freedom. And you're going to find that the p-value then ends up being to 4 decimal places, 0.0003, which is much smaller than the alpha of 0.05. So we are going to reject H naught, and my inference is going to be that there is evidence that the two methods are different. Now I can do that in my calculator. If let me just clear something out here and show you how to do this. You might want to follow along and practice this, okay? So what I've done, let me show you what I did in my calculator. I have put, see if that gets some light there. There we go. I have put the first column of data, this Karlsruhe method, into list 1. So I put this in list 1 in my calculator. I put this in list 2, and then I put this in list 3. Let me show you how to get list 3. So here's list 1, list 2, and I wanted to do the automatic difference. So if I just take my cursor and I highlight L3, I can actually put in a formula for L3 right here. So I'm going to put in the formula list 1 minus list 2. So I do second function 1 because there's a blue L1 above it, minus second function L2 because there's a blue L2 below it. And when I hit enter, it will generate that entire column for me. And you can see that it'll be exactly the column that I showed on the paper here, 0.125, 0.159, and so on. So I'm going to be performing a t-test on this column, not on the original data. I use the original data just to generate the column. So now what I can do is I can go to stat, I can go to tests, I can go to t-test. It's a simple t-test. And then because I have data, not crunch statistics, I press the data. Mu naught is actually in the calculator. Instead of mu naught, we're going to input delta naught. So that's 0. And I'm sending it to list 3, and I'm doing a two-sided hypothesis test. And when I hit calculate, this is what I get. I get my test statistic of 6.0819. I get my p-value, which is to 4 decimal places, 0.0003. It gives me my, my sample mean. So instead of x bar, what we're doing is it's going to be a d bar. And instead of s sub x in the calculator, that's actually going to be s sub d. I mean, these are all equivalent. I'm just showing you what the notation is. And so therefore, s sub x, which we did over here, is s sub d, which is 0.1357. So that is how you do a test of hypothesis on the mean difference, not the difference between means, but the mean difference. Now, what if I wanted to do a confidence interval on the mean difference? So this wouldn't be called the paired t-test, but this is just how we get the upper and the lower bounds. Well, they look very, very similar to what we would have done in chapter 9 for a t-test. So again, d bar in the calculator is going to be x bar. Oh, shoot, did this wrong. Right, we're going to use d bar instead of x bar. We're going to use sd instead of x, s sub x. Yeah, I'm trying to stick with what I was doing here. So not x bar, use d bar. Not s sub x, use sd. And that's about it. So here are your formulas. Obviously, we're going to use an alpha over 2 if it's a two-sided confidence interval. If it's a one-sided lower or upper, we're going to be using just t sub alpha. So let's go ahead and do an example here. And again, you might want to put this in your calculator like I did. So here we've got a situation where we are looking at, oh, that's a good year. I was born that year. The time in seconds for each person. So when it says subject here, we're actually talking about people. So maybe this is, I'm going to go alphabetically. Maybe this is Abe, and maybe this is Bob, and maybe this is Cal, and maybe this is Deb. So these are all people, and there's 2 different treatments. So my 2 treatments are these 2 different cars, car 1 and car 2. And they're trying to see if, because they both have different wheelbases and turning radii. So they put Abe in car 1 and see how long does it take you to parallel park. I don't even know if you have to learn how to parallel park anymore because cars are smart, but in 1962 they weren't. And they put Abe in car 2 and said, well, how long does it take you to park in that car? So what they want to know is, what is the confidence interval on the difference between, or the mean difference here? So I'm going to take and I'm going to compute this column here, this D sub J column. So again, how do we get this 19.2? Well, we would get that by taking, for Abe, the turning radius of 37 minus, I'm sorry, for the parking, these are all in seconds, by the way. So seconds and seconds. So it'll be 37 seconds minus 17.8 seconds on the second car, and that equals 19.2 seconds. And what I want to do is get an upper and lower bound here. So I can actually just use something, again, this is from chapter 9. I'm just going to use a t interval on this column. So once I've generated this column, I am not going to be looking at this data anymore. So what I have done in my calculator, similar to the last example, is I've gone in and I input car 1 into list 1. I'm sorry, I put it into list 4. I put car 2 into list 5 because I wanted to save the data. And then I generated for list 6 the same way I generated list 3 for the previous example. So let me show you what I've got in my calculator here. So here I've input car 1, car 2, all 19 values. And now I want to generate this difference column here. So I'm just going to go to list 6 and say, take list 4 minus list 5. So I'll do second function 4 minus second function 5. And then that's going to generate this column for me automatically. This is just kind of a nice little feature on an exam or homework, so you don't have to, you can make a typo, pretty easily, or an input error. So now what I'm going to do is I'm just going to do, I could do a hypothesis test on this if I wanted to, but I don't have to. I just want to get L hat, and U hat. So now I can go to stat. Well, I could actually just punch these in on my own if I wanted to. In fact, maybe I should remind you how to do that. If I wanted some of the values that I need here, let's just remind myself of the values that I need here. I know that D bar, oh, I'm sorry, I'm doing a totally different problem. Let's just run some statistics on this, then we'll plug in the numbers, and then I'll show you how to use it. Let's just do that. So let me go to one variable statistics here, and I'm going to go one variable statistics on list 6. So second function 6. So it's going to give me the average of this column here, and that is going to come up as X bar. So that's going to be 2143. And my sample standard deviation of the mean difference will be read as S sub X. So that's 12.6849, 12.6849. And we know that my N, what is N here, is 14. So we've got that. Oops, can't see that. There we go. And what else? Oh, and the other value that we're going to need, we know that alpha is going to be 0.05. So I'm going to need T of 0.05 divided by 2, comma, 14 minus 1. And we know how we can get that. We can get that by doing the inverse T function, telling it the area below, which is 1 minus. And then for 13 degrees of freedom, I actually have not done that. So let me just do that. So to get that, we would go second function, distribution, inverse T. If you don't have inverse T, there is a code for it under the general information section on our Canvas. You probably have it because you would have needed it for chapter 9. And so we're going to go 0.975, comma, 13. And that will give me this value here, which will be 2.1604. So now I have all of the components that I could plug in here, right? So this would be 1.2143 minus 2.1604 multiplied by 12.6849 divided by the square root of 14. And then this is just the upper is just going to be this equation, but with that term added. So we'll have 1604, 12.6849 divided by the square root of 14. And you might want to pause it here and verify my numbers. And this will end up being a minus 6.11. And then the upper bound is going to be an 8.5383. And so how do we interpret this? This means that, we'll write it this way, the interval minus 6.11 up to 8.5383 contains the true mu d with probability 0.95. That means there's a 5% chance that it doesn't, right? Now, also remember this. Also, here's another nice little factoid. Had we done a two-sided hypothesis test on mu d with delta naught equals 0, what would we have done? We would have, and here's the hint, 0 is in here. So because 0 is in the interval, we would have failed to reject H naught. Right? Because what am I talking about? A two-sided test would have been this. We would have said mu d equals 0 against mu d not equal to 0. And since 0 is in the interval, we would have failed to reject H naught. So you've seen that before, and it's not the last time you're going to see it. Not the last time you're going to see it. Okie doke. That ends this part. I think it does. Let me double check here. Yes, it does.